Hi everyone. We are going to finish chapter 4 in this lecture, and we're going to start off with this particular slide. And you might be wondering why I have the Wicked Witch of the West pictured here. And no, it's not meant to represent me. It's meant to represent changes in variability or dispersion. And I'll explain that in a minute. But I'm going to use this slide to kind of recap what we learned so far about variability. So I'm going to do it by showing you how we visualize variability with graphs. So let's pretend that this is a frequency distribution. In fact, all of these are frequency distributions. So we have all the possible scores down here on the x-axis. And on the y-axis, we have frequency. Of course, you're not seeing the y-axis because these are just hypothetical distributions that I've drawn here. But what we can see from this first one is that whatever this score is down here on the x-axis, everybody got that same score. All right, so it's just one column of data. There's no variability. Everybody scored the same. So last class we learned about, different ways that we might measure this variability. And we said that, well, we could calculate the range, max minus min. But if we do that, since everybody got the same score, when we do max minus min, well, the highest number and the lowest number are the same number, right? So if all the scores are 13s, 13 minus 13 is 0. So the range here would just be 0. And that would be an accurate representation of this data because there is no variability. We talked about mean deviation and absolute mean deviation, variance, and standard deviation. So with those three other ways of measuring variability, I'm going to use these two distributions, okay? But just note that if there's no variability, all the scores are grouped or clustered on the same score, the same number, and so there's no variability. Now over here, we're beginning to see some variability. Why? Because whatever this score is, that's where most of the people are, right? They're clustered around or clumped around this particular value. But we can also see that there are other scores being represented. Remember, this line is frequency. So we can see that these scores are associated with pretty high frequency. So there's quite a few of these scores. Similarly, there's quite a few of these scores at this end of the continuum. But there's not a lot of these scores out here. So we don't have a lot of outliers. All right, let me just put my phone here on Do Not Disturb. Okay. All right, so here we see some variability. There's some dispersion, right? So from the mean, which would be located here, we begin to see some scores being represented, and the scores are spreading out from the mean. And then over here, we see even more variability, because even though it's still the case that most people score right around the mean, there's an even larger number of people that are scoring way out here. So that's increasing the variability. If we were to take this distribution, and let's say we measure the average distance that scores are to the mean, okay, so average distance, we would have to take every x and subtract x bar, right? So it's x minus x bar, x minus x bar, same thing over here, x minus x bar. So every x is going to be a certain distance from the mean. Now, if we want the average distance, we would have to add all those deviation scores up, because remember, x minus x bar is a deviation score. So if we were to add up all of our deviation scores and divide by n, that would be the number of deviation scores, the sample size. If we did that, then you would think, oh, that's great. We get an average distance scores are to the mean, which, in this case would be some number, all right? It would be smaller than it is here, so but it would be a relatively small number, except for one problem. So do you remember last time we learned that if you add up all your deviation scores, half of them are going to be negative, half are going to be positive, and when you add them all up, you get 0. Same thing over here. If we did all the x minus x bars, if we calculated every deviation score, if you add them all up, you're going to get 0 because half of them are negative, half are positive. So if we just calculate mean deviation score, we're going to get 0 here and 0 here, which clearly does not represent the variability in the data. So we thought we would solve it by taking the absolute value of every deviation score. So that means that if you're negative, if I can find my cursor here we go. If you're negative, you got a negative value, well, we're just going to treat you as if you're positive. Same thing over here, okay? So if you're below the mean, so if you're on this side of the deviation, this side of the distribution, it means that when we do x minus x bar, you're going to get a negative answer. Over here, x minus x bar, you're going to get a positive answer. But same thing, add them all up and you're going to get 0. So it doesn't matter what you divide by, what your n is. 0 divided by n is going to give you 0. So that didn't work either. We moved to the next possible solution and we said, okay, let's square every deviation score. So when we do an x minus x bar, we square it. And same thing here, x minus x bar, we square it. Now we're treating all the numbers the same, and we're going to get rid of this negative problem because any number squared is going to be positive. So that calculation gave us, when we completed it, gave us the average squared distance that scores are to the mean. And do you remember what that's called? Average squared distance scores are to the mean is variance. And so if we calculated the variance here and here, we would see that on average, scores are further from the mean with this distribution. And so this distribution would have a larger variance. But then we came across another problem, and that is when you square the distances, you're squaring your measurement unit. So if these are IQ scores or, gregariousness scores, I don't know, whatever it is we're measuring here, then the units are squared. So if it's IQ, then the variance is expressed as a squared IQ. And if we're measuring, I don't know, kilometers, then that's a squared kilometer. It just makes it harder for people to visualize when we do that. So we said, well, how do we get rid of the squared units? Well, how do you get rid of any square? You take the square root. So we said, fine, we're going to calculate variance, and then we're just going to take the square root of variance, and that gives us, anybody remember? Standard deviation. So the square root of the variance is the standard deviation, and that tells us the average distance that scores are to the mean. The average distance scores are to the mean. And that's the measure of variability we use the most often. So over here, standard deviation would be pretty small because on average, the scores are pretty close to the mean. Over here, the standard deviation would be larger because on average, scores are further from the mean. So when we calculate standard deviation, that gives us a good measure of variability or dispersion. Here, there's no dispersion. Everybody got the same score. Standard deviation would be 0. Everybody scored the same. Now look at what's happening here. All right, you see how we begin to see scores move away? No longer is it the case that everybody got the same score. We see some scoring below the mean and we see some scoring above the mean. The scores are becoming more dispersed, more variable. Same thing over here. The scores are becoming even more dispersed. not only do we have, most people scoring around the mean, but we have a lot of people out here. Over here in the tails, we didn't have very many people. Now we have quite a bit of people in the tails. So that tells us that the dispersion is increasing. All right, so why the witch? Well, those of you who have seen The Wizard of Oz, which I'm thinking that most of you have, there's a scene in the movie where the Wicked Witch of the West begins to melt. And she goes, "I'm melting." You remember that scene? Well, what happens as she melts? She begins to shrink down and expand out as she melts. All right. In other words, the Wicked Witch of the West is dispersing. So when she was just the Wicked Witch of the West, not melting, she was like this pole. All right. No dispersion. But as she began to melt, and I apologize, this should be a little bit shorter than this, but as she began to melt, she began to lose heat. Well, she began to lose height. I don't know where heat came in. She began to lose height. But, matter is neither created nor destroyed, right? She has to go somewhere. So as she melts, she begins to spread out. Okay, and here she's melting even more. Now, I have another analogy which might make even more sense, and that is the icicle analogy. So imagine that this is an icicle, and although icicles, they actually form from the top of something and down, I flipped it over so you can see, okay? So we're standing this icicle up on its end, and icicles are frozen water molecules, right? And so here this would represent no variability. They're all stuck together. They're one big icicle, all right? Now, look what happens when the icicle melts. Those water molecules, a lot of them are still stuck together, right? Just like here, most people score around the mean. So there are a lot of them, most of them are stuck together, but the ones that have melted are now spreading out. Okay, so these water molecules are spreading out and this icicle is losing height. And then over here, icicle is melting even further. Well, the water molecules need to go somewhere, right? Most of them are frozen here in the center, but a lot of those water molecules are spread out. So you see how we see water molecules dispersing? That's what we're seeing here. All right. We don't get rid of any scores, but if we push down on this distribution, what's going to happen? We're going to see more people in the tails. Okay, we don't lose scores, we're just pushing them out here towards the end. Think of a balloon, right? When you push on a balloon, right, the balloon, the air doesn't go out of the balloon if it's tied. The air doesn't go out. Where does the air go? It goes to either end of the balloon. You're dispersing the balloon. It's no longer just a nice well-shaped balloon. Push down on it and you see dispersion as the air moves into the other parts of the balloon. Okay, so again, this would be no variability, moderate variability, and a lot of variability. So now you should be able to answer the question, which of these distributions is the least variable and which is the most? Well, if you remember what these distributions look like, mesokurtic is right in the middle. So these are all normal distributions. They're normally distributed. And mesokurtic is considered to be the middle, neither too peaked nor flat. Leptokurtic is a very peaked distribution, and platykurtic is a very flat distribution. All right, so we go from in the middle to both extremes, very, very peaked, very, very flat. So which one do you think would be the least variable? Well, if it looked like this, no variability, we could say that that would be the least variable. But if they're normally distributed, that means that there's going to be some variability. Because remember the shape of the normal distribution, right? It kind of, I'm going to draw it here, kind of looks like that. All right, so it looks like these, but the mesokurtic is in the middle. So which of these would be leptokurtic and which one would be platykurtic? This one is leptokurtic. Why? Because it's a little bit peaked than the normal distribution. This one is platykurtic because it's a little flatter than the normal mesokurtic distribution. So when we say which one is the least variable, it would be the one where we see the most clustering, and that would be this one, leptokurtic. Platykurtic would have the most variability. Okay, so least variability is leptokurtic because there's the most clumping or clustering. And then platykurtic would have the most amount of variability because we see the most dispersion here. All right. Now, I don't really have a mesokurtic distribution shown here, but mesokurtic would be in between. Okay, so in between this one and this one, we have mesokurtic. So if we were to order these from least variable, we would start to leptokurtic, most variable, platykurtic, and in between, mesokurtic. All right.